In today's lesson, we're going to be looking at derivatives of trigonometric functions. We want to show that the derivative of tan of x is secant squared x. Recall that the tan of x is equal to the sine of x divided by the cos of x. So therefore, taking the derivative of tan of x, if we don't have that yet, the way we would go about doing this is treat this as the quotient rule. So this will be the bottom times derivative of the top minus your top times the derivative of the bottom, all divided by the bottom squared. In which case, this becomes cos squared x plus sine squared x over cos squared x, which cos squared x plus sine squared x is 1, and therefore that's equal to 1 over cos squared x. Recall this is equal to 1 as cos and sine are defined about the unit circle. And therefore this is 1 over cos squared x, but we know that this is equal to your secant squared of x, because by definition, secant of x is 1 over cos of x. So keep this one in mind. Obviously, you don't want to have to do this every single time you want to take the derivative of the tan of x. It's a fairly common trig function, so commit this one to memory. But if you are stuck, you can easily produce it. Let's try another. This is another common trig derivative. Derivative of cosecant x is negative cosecant x cotangent x. Let's take a look at why. Well, the derivative of cosecant x is equivalent to calculating the derivative of 1 over sine of x, because by definition that's what cosecant is. Well, we could treat this as the power rule, and in which case when I take my derivative, I drop down the minus 1, subtract 1, and take the derivative of the inside, in which case we get cos of x. So this ends up being negative cos of x over sine squared of x. Now to get this relationship here, negative cosecant cotangent, I'm going to go ahead and break this up into negative 1 over sine of x times the cos of x over the sine of x, which is equal to 1 over sine of x is cosecant x, so this will be negative cosecant x times cotangent x. And therefore we have proven this derivative. Let me show you some other common derivatives. You might want to copy these out here. These are your common derivatives. In the previous lesson, we had proven these two results, and I've just taken up this one and this one. These two here I'll leave for you to try out. Feel free to take the derivative of secant of x, which is 1 over cos of x, and prove this result, and likewise for cotangent. So these are our common derivatives, and you'll see them used quite often. Let's take a look at applying some of these. So for our first example here, we want to take a look at finding the derivative of this function. Well, this function here, we can rewrite this as 1 plus the tan of x to the negative 1. Therefore, when I take my derivative, we're going to drop down the 1, and subtract 1 gives me negative 2, and then the derivative of the inside, well, the derivative of 1 is 0, and the derivative of tan of x is secant squared of x. So cleaning this up a bit, we get negative secant squared x over 1 plus the tan of x quantity squared. For the following question here, we want to find dy dx. So taking our derivative here, we're going to have to go ahead and do the quotient rule. So we're going to have here the bottom times the derivative of the top is 1 minus your top, and the derivative of the bottom is going to be cos x minus sine x, all divided by the bottom squared. Now we can clean this up a bit here. I can go ahead and obviously drop the brackets on the first expression because you're just multiplying by 1. Distribute the x. The bottom I can expand it out, giving us sine squared x plus 2 sine x cos x plus cos squared x. Continuing on here, I can collect up like terms in the top, so I can factor out a sine of x, in which case we get 1 plus x, and factor out a cos of x, in which case we get 1 minus x, and take the entire expression. And now we know sine squared x plus cos squared x is 1. So a slightly more simplified derivative would look like this. As an interesting challenge question, can you find the values of x such that the derivative is 0? All right, for the next example here, we're going to go ahead and take our derivative. So the main function here is cos. So the derivative of cos is negative sine, in this case of tan x. Now you go ahead and take the derivative of the inside. Well, the derivative of tan, as we just discovered, was secant squared of x. So cleaning this up, my derivative would be negative secant squared x times the sine of tan x. For the next question here, we want to find the equation of the tangent line to the curve at the point pi over 6 and 1. So equation of the tangent line, we need to find our slope. So we're going to go ahead and calculate our dy dx. In this case here, we'll get cos of x minus the sine of 2x times the derivative of the inside, which is 2. And then we're going to go ahead and evaluate that when x equals pi over 6, in which case here we get the cos of pi over 6 minus 2 sine of pi over 3 after simplifying. Evaluating these, we get the cos of pi over 6 is root 3 over 2, and the sine of pi over 3 is also root 3 over 2. Subbing this in and subtracting, we end up getting that the slope is negative root 3 over 2. Therefore, to find the equation, we can sub it in. Subbing our point in here, we get 1 equals negative root 3 over 2 times our pi over 6 plus that y-intercept. And solving for our y-intercept here, 12 plus root 3 pi over 12. So we have our y-intercept and we have our slope. And in this case here, the answer is y equals negative root 3 over 2 x plus 12 plus root 3 pi all over 12. So for this question here, we're given that f at x is the cos of x. We want to find the 27th derivative. Again, if you're not familiar with this notation, this represents the nth derivative. So the function, and then with an exponent in brackets of an n here, would represent the nth derivative. So therefore, we're looking, in this case here, we're looking for the 27th derivative. Obviously, it's not intended to take the derivative 27 times, but we want to find if we can establish a pattern here. So let's take a look here. I know that f at x is the cos of x. Okay, well, f prime at x is negative sine of x. Continuing, f double prime at x is going to be negative cos of x. F triple prime at x is going to be sine of x. If I go ahead and take my fourth derivative at x, I end up getting the cos of x. And now notice, once you hit back to your original, that sequence will now continue on. Now I know in this case here, if I take my fifth derivative, we're going to get negative sine of x. Likewise, I see my sixth derivative will end up being negative cos of x. Your seventh derivative here will end up being the sine of x. And you'll notice here on the eighth derivative, it goes back to the cos of x again. So you can notice here the pattern that we start off with our function f at x, and then it goes to first derivative, second derivative, third derivative, and then it'll actually cycle back, and you can see here that this initial function, the 0th derivative, the 4th derivative, the 8th derivative will all be cos. And likewise, the first derivative, 5th derivative, 9th derivative will all be negative sine of x. The second derivative, the 6th derivative, notice here this goes from 2 to 6, so you're adding 4, so then we go to the 10th derivative, etc. To find out where 27 lands, the only thing you have to do is take 27, divide it by 4. Well, how many times is 4 going to 27 evenly? That's going to go in 6 times. And you're going to be left with a remainder of 3, which means that the third derivative, in this case here, is where the 27 will land. So f at 27 of x would have to equal the sine of x. So notice once we've established the pattern, we can now answer this for anything. I could ask you the 99th derivative, 103rd derivative, 2000th derivative. Really doesn't matter. Once you establish the pattern, you can kind of see where everything would land. In this example here, we want to find all points on the following curve where the tangent line is horizontal. So in this situation here, we take our derivative. So dy dx in this case is going to be 2 cos x plus 2 sine of x cos of x, and we're going to set that equal to 0. So we get 2 cos x plus 2 sine of x cos of x. So I want to find values of x such that this is 0. So I'm going to try to turn this into a product, try to factor this. So I'm going to factor out a 2 cos x out of this. and I end up getting 1 plus sine of x. In this situation, we have two options. Either 2 cos x is 0, in which case cos of x is going to be 0, or 1 plus the sine of x is 0, in which case the sine of x is going to be negative 1. So recall our unit circle here. You'll notice that the cos of x is going to be 0 at pi over 2 and 3 pi over 2. I'm going to make the assumption with this question that they're going to restrict the domain from 0 to 2 pi. It wasn't stated in the question, but I want to add that to this question. It can be answered without restricting the domain, but I want to tackle this problem as if the domain just goes from 0 to 2 pi. So in this case here, one complete rotation around the unit circle only gives me two answers for the cos of x being 0. That's going to happen when x equals pi over 2 and 3 pi over 2. Next we have, when is the sine of x going to be negative 1? Well, the sine of x is going to be negative 1 at 3 pi over 2. So that doesn't give us any new x values here. So they want us to find all points. So that's just a matter of subbing these x values into our original function. When x equals pi over 2, we want to find the corresponding y value, in which case this is going to be 2 times 1 plus 1 squared is 3. And with the next one here, we want to evaluate this one here. So 2 times sine of 3 pi over 2 is going to be negative 1 plus negative 1 squared, in which case we get negative 2 plus 1 is negative 1. So the 2 points where the tangent equation is horizontal on our curve, 2 sine x plus sine squared x, is going to be at pi over 2 and 3, and at 3 pi over 2 and negative 1. Let's take a look at the next question. For this question here, they want us to show that the following function is always increasing on the interval 0 to pi over 2. Well, let's take a look at the derivative. So f prime at x is going to equal secant squared x minus 1, in which case if we rewrite this, this is going to be 1 over the cos squared of x minus 1, which is 1 minus cos squared x over cos squared x. Now to show that this is always increasing, I need to show that this is always strictly greater than 0 on the interval 0 to pi over 2. You'll notice on the unit circle from 0 to pi over 2, your cos function will always be greater than 0 and less than 1. Therefore, if I square that number, since it is a number between 0 and 1, therefore I know cos squared of x will also be between 0 and 1. And therefore I know here the bottom is always going to be positive because you're taking the cosine of x and squaring it. The top, you're taking a number that's going to be less than 1, and you're going to take 1 minus that number, in which case this expression here will also be positive. So therefore we have a positive number divided by a positive number, and in which case here, your first derivative is always greater than 0 on this interval, and because of that, the function is always increasing. That concludes today's lesson. Thank you.